Hello, my name is Jörg Dahlheim, and in this talk, I'm going to present you rkt-io, a direct I/O stack for trusted execution environments. When we look at common cloud deployments, the question is, how can we secure the user application from both the cloud provider as well as other tenants in the host? Luckily, if you look at what modern CPUs provide, is that they have something called trusted execution environments, and also major cloud providers give them to their users. So if you look at the trusted execution environment, it will allow to run our application in a protected environment where the operating system running the same host and no other user can access that. However, when we want to do I/O, for example, a read syscall, we have to first switch into some unprotected mode. This is so-called world switch. Afterwards, we can actually do the system call. Then when the operating system returns from the system call, we have to perform another world switch in order to return the result into the application inside the trusted execution environment. It turns out that this world switch is 5 times slower than the actual system calls. So to counter that, in the past, there have been other mechanisms proposed, so-called switchless design. I just want to introduce 2 major ones here. So one is based on the host operating system, and the other one is based on library OS. The host operating system works as follows. So you have your applications running inside the trusted execution environment. And when the application wants to do I/O, it has an asynchronous interface in which system calls gets queued into a memory buffer outside the trusted execution environment, and a thread outside will then process these system calls and then put the results in another system call response queue. Library OS works a similar way. However, it usually puts more functionality of the operating system inside the enclave and only depends on very low-level interfaces such as tab devices or block devices. Both these approaches valid, and they also world switches. However, they still have some problems with respect to high performance I/O. So the operating system in both is still on the I/O path, and they both require I/O threads that run outside the trusted execution environment, and these require tuning. Then we also have data copies because we need to copy data first out of the trusted execution environment into unprotected memory before we can actually give it to the operating system. And in the case of library OS approaches, they often only implement a subset of the Linux API, so there are some porting required to run these applications in these environments. With rkt-io, we want to present a novel design that where we combine a library OS with direct I/O libraries. So this works as follows. So you have your application, it runs inside the trusted execution environment, and it uses the system call interface to talk to a library OS that's running inside this trusted execution environment. This trusted execution environment has full Linux API compatibility, which we will show later how. And it also instead of having the host operating system, uses a direct I/O interface, which allows it to communicate with hardware such as NIC or storage hardware directly over host memory without any other participant in the middle. And this allows us to bypass the host operating system and do some other performance optimizations, which I will explain later. So just as a motivation here, we did a benchmark with this setup. So you can see here on the x-axis 4 different setups, and on the y-axis the time. So we have the system call send to, and we implemented both synchronous and asynchronous system calls as well as direct I/O, where you directly access the hardware. And you can see that synchronous and asynchronous system calls are slower than the direct version. So we can gain performance from having this approach in place. With this, I want to explain a bit how all these things are designed. And this is divided into 3 parts. So first we have the I/O stack, where I show how everything is composed. Then I want to explain how hardware events are processed. And later, I want to show how we optimize memory handling, buffer handling. So in order to become independent from the host OS, we use the following stack. So for network, we have DBDK. This allows us direct access to the network hardware. But there's a downside, there's no TCP/IP stack in DBDK, and there's also no socket interface, therefore. And then for the storage side, we use a thing called SBDK, which is a way of accessing NVMe drives, so block devices, directly from user space. But also here, there's no file system support and also no file abstraction. So the question is, with these low-level interfaces, how can we maintain compatibility for existing applications that expect PostX API? And the answer is here. We have libc in place, which is the application linked against it at runtime. And this allows us to maintain a full compatibility to existing existing applications. And this is achieved by also linking a library OS into it, which is based on Linux. So it's a Linux port, and it can be linked as a library into the trusted execution environment. And it's called ACL. And this stack gives us also the Linux network stack, as well as the file systems that are in Linux. Then under these, this library OS, we implement DBDK and SBDK as drivers. So based on DBDK and SBDK as mentioned before. And those then allow us to bypass the host, and we can gain direct access to hardware. So now a bit about how we handle interrupts from the hardware itself. So traditionally, you have when you have, for example, network driver, whenever there's new events, for example, data has been processed from the sending queue, or there's new data in the receive queue, then will send us usually interrupts. However, we cannot really use those in our setup because interrupts would cause word switches, and this is what we want to avoid. So instead, rkt-io uses polling, which is also something, by the way, that many high-performance network driver do these days anyway. So when something is sent from the TCP stack, it goes straight to the network queue of the NIC. However, there's also a polling thread that watches both on the receiving and sending queue of the network card. And when there's new data coming from receiving queue, it's passed to the TCP stack, and as well when the sender queue is getting empty, then so the TCP stack gets notified about that. And this works then for the block device driver similarly, and this is how we can handle I/O events in an efficient way. Lastly, I want to talk a bit about the I/O stack partitioning, how we optimize the data path. But first, let me explain for that how applications would use this API. So when they want to write something out, we need to do a copy of their data into the libOS. And because when we return to the application might reuse the write buffer. And we cannot write everything straight to the block device because that would be quite slow. And that means that in the naive implementation, we would need to perform a second copy when we actually want to write things to the NVMe drive or the network device. So the question is, how can we avoid this second copy? And the approach was as follows. So here you see the TCP stack again. In the naive design, we would have two copies, and both from the TCP stack to something called a socket buffer, and then in a second copy, it would be copied to the actual to the unprotected memory where the network card can read it. In our implementation, we re-architected the TCP/IP stack to allocate these socket buffers outside of the trusted execution environment in unprotected memory. And then when we actually pass the socket buffer to the hardware, we no longer need to do a copy because we can just reference that. And this way, we can also optimize the I/O for the page cache, where we put encrypted blocks directly to unencrypted memory, and therefore save copies. Now that I explained to you a bit about the design, I want to go a bit more detail into how app developers can use that. So the way that rkt-io works is that there's an application image that is based on X4, where the applications are packaged. And at runtime, the master libc replaces the originally linked libc library inside this file system image. And the I/O path can be also encrypted using cryptsetup for block devices or a layer 3 VPN for the network part. And this allows applications to be easily ported. If you have something like Alpine Linux, you can just package it like that. Yeah, after you saw them how we evaluated this thing, now I want to explain how we evaluated it. We have several benchmarks. For instance, we have synthetic benchmarks where we measure storage and network performance. And then we also have in the paper a series of real-world applications such as SQLite, Nginx, Redis, and MySQL. And as the baselines, we have the non-secure version. So this is a native Linux application running on the host. And then for as a representative for the host OS approach, we took Scone, and as approach for the library as version, we took SGX-AKL. So here is the results for the network stack. So you can see on the y-axis the throughput in gigabits per second, and on the y-axis the different systems. And you see that between SGX-AKL and Scone and our system rkt-io, there's a 9x speedup, and this is mainly also to efficient use of NIC offloading, where we can increase the I/O throughput. Then similarly for the storage stack, here we have FIO performing a random write. On the y-axis, you can see the throughput in megabytes per second, and on the x-axis, you can see the different systems again. Here we also have 7x speed up over the existing systems. However, there's still a lag behind native. Native, for instance, has a way bigger page cache, while in the current implementation of Scone of SGX that we had for evaluation, there's a limitation in how much memory you can allocate within the enclave. So we cannot keep up with native in this case. But this is a limitation that's going to be removed in the future. Now, just one application that we also benchmarked, which was somewhat surprising to us. So we run system bench on MySQL, and we saw there's this huge gap between rkt-io and even native. So here you see on the first graph on the y-axis the throughput, and then on the second graph you see the latency. And we see here that SGX-AKL and also rkt-io is both faster than native and Scone. And we looked a bit into the reason why this is the case. So we looked at what system calls MySQL performs in a native execution. And we saw that the Futex system call is used a lot to log different tables when performing queries in MySQL. And in our implementation, Futexes are implemented within the library OS, so context switches are cheaper this way, and this benefits our application in this case. So with this last result in mind, I want to conclude my talk. So what we've seen today is that current SGX implementations are not designed for high performance. They still have the operating system on the as a bottleneck. They need I/O threads that need to be tuned. They have additional data copies between the trusted execution environment and I/O threads on the host operating system. rkt-io, on the other hand, provides fast and direct access to I/O devices. We can maintain Linux API compatibility to existing applications. And we also publish the source code so you can try it out yourself and reproduce the results from our paper. Thank you for your attention, and this is all from